A sequence is a function from the natural numbers to any set. So we take as an input a natural number and return as an output anything in the set S of n. When we talk about a sequence, this particular type of functions, instead of using the regular notation of functions, we use this particular notation for sequences. When we say Sn, we mean actually the image of the number n, the output corresponding to the input n. So, for instance, let's see this example. Let's see the sequence defined in this way. Sn equals n squared minus 1. So, with this formula, we are given the values of this sequence for any value of n. So, for instance, S0, that will be, to substitute here a0 and do this operation, right? That will be 0 squared minus 0, which is 0. So the first term of this sequence, S0, is 0. S1, well, we do the same. We substitute, we put 1 here in place of n, and so we obtain here 1 squared minus 1, which is 1 minus 1, which is 0 too. So the S1 is going to be 0. How much is S2? We substitute 2 here. We are going to get then 2 squared minus 2. 4 minus 2, which is 2. So we obtain in that way S2. So in that way we can obtain any term of the sequence, right? S3, S4. So this is an infinite sequence. We obtain S0, S1, S2, S3, S4, S5, and we can keep going until infinity with this formula. Another way to define a sequence, instead of just giving the formula of the function, is this one. This is a very particular and interesting way to define a sequence, which is defined in terms of other terms of the sequence. So, for instance, in this case, this sequence is defined in this way. The term Sn is equal to 3 times the term Sn minus 1. That is the previous term. And the first term of this sequence is 2. So this is the data of this problem. So we know how to construct the terms starting with the one given, right? So we were given that S0 is 2. So how much is S1? Well, we look at this definition here. We were told that Sn is equal to 3 Sn minus 1. So that means that S1 will be 3 S0, right? So 1 is defined in function of the one before, so that's what means this in here. And as we know that S0 is 2 because that was given, so we know that S1 is actually equal 3 times 2, and this is 6. So we have now that S0 is 2 and S1 is 6. How much is S2? We follow the same definition. S2 is going to be equal to 3 times S1. 3 times the one before. The one before is the one that we just obtained, the 6. So, 2 will be equal 3 times 6. So, that will be equal to 18. So, this is a case in which the sequence is defined by recurrence. So we have that this way to define is a direct way, and this way to define a sequence is a sequence given by recursion. Sometimes it's easier to find the terms of the sequence in one way or the other. In general, when we have the direct formula, that's what we want. Sometimes when we have the recursion formula, we can do transformations until we get from the recursion the direct form. The direct form also is called closed form. And so sometimes we would like to calculate, having the recursion form, calculate what is the closed form of that particular sequence. Let's see another example. So let's see this sequence defined by recursion in this way. The term n is equal to 7 times the previous term minus 12 times the other previous term. I mean, if this sequence, this definition go 2 terms back. So if we have all the terms of the sequence, each one is defined in terms of the one before and the one before. So the n minus 1 and the n minus 2. So the n depends on the n minus 1 and depends on the n minus 2 too. In those cases, we are going to have the 2 first terms, otherwise we cannot find the third. So that's why in this case we have given S0 and S1 too. So let's see how to calculate each of the terms with this data. So to calculate the second term, S2, so following this formula, we are going to have to write 7 times the one before. The one before of the 2 is the 1, right? So it will be 4 minus 12 times Sn minus 2. So if n is 2, n minus 2 is 0, right? So 2 will be 4. So that will be times 4 because S0 is 4. And then we have so far that 0 is 4, S1 is 4, and S2 is minus 20. So when we calculate now S3, remember that S3 is going to be in function of the one before and the one before. So we can calculate it as 7 times minus 20, that was the one that we just calculated, minus 12 times the one before, that was 4. In that way, we find that S3 is minus 188. And in that way, we can calculate them all, right? So it's 2, 3, 4, 1 by 1. In opposition to what would happen if we have the direct form. If we could have that Sn is equal some function here of n, and in a direct way, we would be able to calculate Sn for any n directly. So for instance, we want to calculate how much is S101. Well, if we have a formula here, we can plug in the n and we will calculate the term 101. Instead, if we have a recurrence relation like this, in order to get to the 101, we will need to calculate all the terms before until we have that S100 and S99, that are the two that we need to calculate S101. So because of that, our goal is going to be find a direct formula. I mean, when we have a formula given by recurrence, find the direct formula of this one. And now we will see a very famous sequence defined by recursion, the Fibonacci sequence. In the 13th century, the Italian mathematician Fibonacci posed the following puzzle. Let's say the rabbits are able to mate at the age of 1 month, and pregnancy takes 1 other month. Thus, at the end of its 2nd month, a female can produce another pair of rabbits. Let's suppose also the rabbits never died and a mating pair always produce 1 new pair, exactly 1 new pair, 1 male and 1 female, every month from the 2nd month on. With these rules in mind, the question is, if we start with a new pair from birth, how many pairs will there be in 1 year? So now stop a moment the video and think for a moment if you can figure out the answer to this puzzle. Well, Fibonacci did figure out the solution, just counting here the rabbits. So in the 1st month we have only 1 pair, and they are not mature yet, right? You see that it's drawing with a lighter shade when they are not mature. In the 2nd month, we have the same pair, but now they are mature. In the 3rd month, we have the same pair, but now they have a new pair. This new pair is just born, so it's not mature yet. In the month 4, we have the one that we used to have. This one now became mature, and this one that was producing rabbits now produce a new pair. In the month 5, we have still the 3 that we used to have before, right? Only that this one mature. And also these pairs here that were producing rabbits are still producing in this month. So in the month 6, again, we have all the ones that we used to have. They are still there, only that the ones that were not mature become mature in this month. And the other 3 that were producing rabbits still produce 1 pair each. So observe the sequence of numbers that we are obtaining. In the first month, we got 1. In the second month, 1 pair. In the third month, 2 pairs. In the fourth month, 3 pairs. In the fifth month, 5 pairs. In the sixth month, 8 pairs. And I think that you can keep figuring out, right? So what will happen at the 7 months, 8, 9, 10, 11, and 12? That was the question of Fibonacci. Well, if you figure out that, putting here all the values until 12, you could answer that the final amount of rabbits will be how many? Stop again and count how many will be in the month 12. Instead of counting, you can also try to figure out what is going on with these numbers here. So this is 1, 1, 2, 3, 5, 8. Do you see any pattern here? Well, what's going on here is that each number is equal to the addition of the 2 previous. So 2 is 1 plus 1. But 3 is 2 plus 1. And 5 is 3 plus 2. And 8 is 5 plus 3. So you can figure out how many is going to be in the month 7, right? So it's going to be just 5 plus 8. So it's going to be 13. And so you can figure out in the months 8, 9, 10, 12, and 11, and 12. The way that we write this as a Fibonacci sequence could be to say that the end term of the sequence is equal to the one before plus the one before, just the addition of the 2 previous one. If the one that you are is n, the previous one is n minus 1, and the one before is n minus 2. So it is a sequence given by this formula. Each term is equal to the addition of the 2 before, and where the first and the second terms are 1. And so in that way, we can see that the next one, if 1 is 1, if 2 is 1, F3 will be 1 plus 1, which is 2. And so F4 is going to be 2 plus 1, which is 3. And so F5 is going to be 3 plus 2, which is 5. And so on. You can figure out then all of them until F12, and you can answer the question of Fibonacci. And in general, you would like to know how much is Fn. So in general, we will try to find out what is the direct or close formula for this that tell you exactly how much is Fn, depending on n, and not depending on the 2 previous ones. Fibonacci numbers appear in nature and in many other places. For instance, one interesting example in nature is a pine cone. This is the back of a pine cone, and what you can observe in any pine cone is that if you count these spirals, starting at any one, for instance, starting, let's say, at this one, I count 1, 2, 3, 4. If you count all of them, the ones that are marking here in green, you will see that they are 13 in this case, right? So in this drawing, when I count the spirals in this direction, are 13. If I count the spirals in the other direction, all the spirals that we have here, let's count, starting with this one, for instance, 1, 2, 3, count them all, and you will see that they are 8. So we have that in counting the spirals in this direction are 13, and in this direction are 8. These are 2 consecutive numbers of the Fibonacci sequence. And what happened is that in any pine cone that you can find in nature, the spirals in one direction and the spirals in the other direction, they are always two numbers of the Fibonacci sequence. Sometimes it will be like 5 and 8, sometimes it will be 8 and 13, sometimes 13 and the next one. So no matter what number is, if you count in one direction, the other direction will be the next Fibonacci number. And as well as in nature, appear in many ways, in other plants also appear the same pattern, for instance, in sunflowers, artichokes, pineapple. So if you count in any of those, if you have one that you can look at right now, count, and you will see that in one direction or the other, there are always two consecutive numbers of the Fibonacci series. Also, in some spirals, like the Nautilus or also any other seashells, appear also numbers of the Fibonacci series. You can see also applications in architecture, in art in general, since this is related to the golden ratio that you may have here of, and it has many applications also in engineering and computer science.